All right, so welcome to part 2 of section 5.3. So first off, we're going to write a definition, pretty major definition. And this definition is the number E. So if you calculate, if you guys see like the letter E, there's actually a number associated with that. So this is the definition is the number E is defined as the expression of that 1 plus 1 over n, all raised to the n power, where n is 1 or more. Now this may be kind of weird. What does that mean, right? So essentially, right, if you plug in numbers in for 1, so let's say if n equals 1, right, we get a number out just like a function. If n equals 2, we also get, a number. So the question that becomes, we want to kind of estimate roughly where this actually goes if n gets larger and larger. So the question is, well, what happens as n goes to infinity? So in other words, n is an arbitrary, really, really large value. And again, this is a quick, brief introduction into this kind of stuff. You'll be seeing this a lot more in calculus. But essentially, I just want to give you guys a quick concept. As n gets bigger and bigger, if n goes to 1 million, for instance, what does this number actually end up being? Now, the cool thing is, at a certain point, the number doesn't really change as much. It only changes to hundreds of the millionths of a decimal when it comes to it. So essentially, again, we'll talk about this later on in the course, but we'll say is as n goes to infinity, we want to figure out what happens to this function. And believe it or not, this ends up being 2.718 and so forth. It just keeps going and going and going. But essentially, those three numbers or four numbers don't change no matter what happens, how large n is. So if you plug in, 1 billion into here, you're going to get those these four same numbers, and actually probably the same set. I think 7 numbers, no matter if it's a million or a billion, believe it or not. So what we say is, well, this number will always be associated to a letter called E. Kind of like what I is for imaginary numbers, same thing applies here. So E is the actual number, we'll call it 2.718. Or you could just say 2.72 for short. Okay. So again, whenever you see E, you can always associate it as 2.72 to help you guys out. Okay. Now, the reason why this is so important is, well, we can actually graph using this type of stuff. That's the exact same way we graphed exponentials, because technically, now since it's a number, we have a new parent function, just e to the x, okay, which again is the exact same process if we just do a to the x. We do the exact same rules no matter what. Nothing really changes. Okay. So let's just do a quick example so you can see how this would actually work. All right, so let's see what's happening here. So first we're going to graph our parent function. So our parent function is just the e to the x. And we do the same thing. We can graph 2, 1, 0, -1, and -2. And again, if you really want, you can just plug it in, right? So again, you can always give yourself a little note that e is equal to 2.72. So we can plug it in and say, well, how do you square, so forth down the line. So you square this number, gives you, that to the first power, to the 0 power, and so forth down the line. Okay, so I'm just going to give you an arbitrary value. I'm just going to put e squared, e, right? Essentially what that is, it's just going to be 1 no matter what. This is 1 over e, and this is 1 over e squared, right? Again, you could just plug it in to get the actual numbers. But for our case, we just care about what's happening here. Okay. All right, so now if we use this transformation, the same thing applies. We got to figure out, so a is going to be just 1, so that doesn't really count. H and then k. Now this is, so h is going to be opposite of the sign, so it'll be 3. Now h is 0 because there's no ethane added. So technically, The only thing we're doing, so the y's will literally stay the same. We're not adding anything to that, so you could just say plus 0. And then for the x's, we're going to be adding 3. So literally the y's do absolutely nothing. So if we really want, we can just write those down first because those don't change at all. And now for the x's, we'll be adding a 3. So 2 plus 3 gives you 5. And I'm just going to go down the list. Okay. And now we just graph it. Okay. So 5e squared. So that's going to be really high. 4e, that's almost 3. 3, 1. 2 and 1 over e. And 1 and 1 over e there. And again, right, if you want to figure out how far does it go down, we got to write our our horizontal asymptote. So in this case, a horizontal asymptote is the exact same rules. So it's a line y equals 0. So it should not cross the x-axis at all. So it flans out like that. So the exact same rules, right? When it comes to e and exponential, you do the exact same rules. Nothing really changes, okay? That's it. All right, so the last part of this section is, well, a little bit of solving for it. So how do we solve for exponential functions? So one of our most popular ways to solve for exponential function, or expression equation, sorry, is if we have the base equaling the same value. So let's suppose we have a to the v is equal to a to the u. So the base are the same numbers. Therefore, the exponents also equal to each other. Now, this would kind of make sense. Like, for instance, let's suppose I have 5 to the x equals 5 to the third power. Well, as you can see, well, the only number that works is if they have to be identically the same is x must equal 3, right? Again, right, since the base is the same, therefore x has to equal 3. It has no other choice, right? This must be 125. Well, the only way to get 5 to some power to equal 125 is to make it 3. That's what this comes into play, right? So let's try a couple examples using this new equation. So let's suppose we want to solve for x here. Now the problem is, right, we cannot use that because the bases are not the same, meaning 3 is not equal to 81, right? That's not possible. But this is the only way we know how to solve for equations. So what if we try to force the numbers to be the same? So in other words, can I write 81 in a different format? So in other words, can 81 be written as 3 to some power to give you 81? Okay. And well, we could just find out, right? So you can say 3 squared is 9, 3 to the third power is 27, and 3 to the fourth power that gives you exactly 81. So we can. So that means 3 to the fourth power equals 81. So what we can do now is substitute what we have here. So 3 to the x plus 1 is now the same thing as equaling 3 to the fourth power. And now we can use our equation to solve for it. So since the bases are the same, therefore the powers must also equal one another. Or in other words, x plus 1 equals 4 now. And notice now it's a very simple equation to solve for. So therefore, x must equal 3 in order to this be true. All right, so in the next video, we'll do a couple more solvings for us. I think it's like 4 or 5 more that we get used to using this way of solving for it.